So the panel would go out about where the Met station is now, and somebody carrying an ASD would walk out following that footpath. So they would go 500 meters out, turn left 100 meters, turn left 500 meters, turn left 100 meters, come back, go down 500 meters, turn left 500 meters, turn left 500 meters, come back 100 meters, go out this way 500, go left 100, back, left again 500, left again, go out, across, back, and home. And that would be the full notice site. So that's why you see the footpaths. And these are really worn because now there's the ground viewing radiometer across the road. That's part of RADCATS. Ideally, you would place these randomly across the playa. But there's this handy road, and these are really heavy pieces of equipment, and to characterize them as heavy, to carry out the computers to then download the data is heavy, so it was, let's put them someplace that we can get to, that puts them next to the road. And then it was, well, we already have these footpaths that we're using for this motor site, let's put them along there. So that's why you have two here, you have one down there at the end of the Modus transect, and you have one up at the north at the end of the Modus transect. It turns out that's not an unbiased estimator. So there's some issues we're dealing with on the uncertainties of only having 4 sample points and how do you do that. There's some other things we'll talk about during the campaign about the size of the footprint of the instruments and what issues that plays. But when you start walking out there, we'll all walk out basically single file for most of it. And then when we get over there, you'll find areas that you can kind of spread out and don't worry about it. But you know, you can tell if you just start, it is squishy. It gives. So this was the start of RADCATS. You saw the skull. They had a bigger one here for a while. Very good. When we had the idea of automating instruments, one of the things that always comes to people's mind is the safety of your equipment. You're leaving it out. Is it going to get stolen? In Nevada, is it going to get shot? Is it, you know, there's. So we started by placing this Met station near the road, up by where we had the high-resolution test site, and we had it there for a full year. Nothing seemed to go wrong with it, and so then it was, okay, let's move it off the road and let's start doing things in earnest. And we developed some really inexpensive radiometers to start looking at the ground and see if we could keep track of what the reflectance was doing as a function of time. The reason we opted to keep the meteorological data are, one, it's for wind speed, because if it's a very windy day, then you have dust kicking up, and that's something that would be nice to know. And there's a nice correlation between the wind speed and dust. As long as the wind speed is below 10 knots, which is 10 nautical miles per hour, 10 miles per hour basically, you really do not have to worry about blowing dust. And that's a nice, easy marker. Rain gauge was our first attempt to try and correct for any kind of moisture effects. We then followed that up by getting moisture probes, which are more direct measurement. And the idea is that if the surface is wet, you need a different spectral reflectance correction, because the data we were doing for automated collections was multispectral. So to fill in the gaps, you use a model of the surface, and that model is driven by moisture. The other pieces we have is we have a temperature and humidity sensor and a pyranometer. The pyranometer probably hasn't been cleaned in 15 years. It's not an absolute instrument, it's just cloudy, not cloudy. Basic idea. It shows up in the ground viewing radiometer data also. If you have a sharp drop in signal, it's probably because there was a cloud in front of the sun. Even a unclean pyranometer is enough to give you an idea if you have big changes in the irradiance coming from the background sky. So with the cloud conditions we have right now, you would probably see some of that in the pyranometer data, small little wiggles, and it would say, well, this is probably not such a good day. But realistically, most of this is primarily as a qualitative type assessment of, I got a really weird data set, both if I'm on the site, so if, let's say somebody collects data on the site, and then somebody's processing it 3-4 weeks, 3-4 months, 3-4 years later, and they go, this is a really odd data point. They might go back and look at the wind speed, they might go back and look at the pyronometer data, they might look at the surface moisture data. And so as we start going forward and trying to analyze for uncertainties that are smaller than this 2-3% number, we'll start including in wind speed and direction and rain gauge information and pyronometer information as part of the data set to do the analysis to find out where we might have correlations of bad days and good days versus low uncertainties and high uncertainties.
Okay. So it's primarily for looking for uncertainty days, uncertain days.
Yeah, good day, bad day. And you still have to know, for here, a bad day is southwest winds, so basically if this anemometer or the wind vane is pointing in that direction and the wind speed is going at 20 miles an hour, that's a bad day. You don't want to be doing anything with those data sets. Some of the others, if there's a strong north wind, if I saw a strong north wind, I would be looking for the next day, hoping there was an overpass, because everything got cleaned out and it's gorgeous weather and you're going to get a wonderful data set. So there's some other things you can do with it as well. All right? There is no need, this question comes up periodically, there's no need to have balloon sondes for working in the reflected solar. Absolutely none whatsoever. As long as you have a way to get vertical column integrated water vapor. And that you can get from a solar radiometer. You can even get it from a GPS unit. What the balloons give you is vertical profiles of information. In the solar reflective, the only thing you really have to know about from a vertical profile standpoint, definitely at the 2-3% and at the 0.5 to 1% also, is big layer of absorber and big dust layer. And are they on top of each other or below each other or at the same level? So it really comes down to is, do I have a volcanic eruption and is it above or below the ozone? Everything else, it's a small little problem. As long as you have total column water vapor, you're fine.
This is called?
Oh no, that's the, sorry, this is the transmitter to the Wi-Fi. Yeah.
And you got two temperature gauges on there?
I think they have, and I'll have to ask Jeff. I think this one may be inoperative. This is now 15 years old, and there's no way they should still be using a 15-year-old hygrometer. So I suspect they just put a new one in. I probably could even check to see if this one may be disconnected. The two things not to do are stand in front of this and stand in front of that when it starts to spin, which it may start to do. And we can spread out because it's not going to cause any problems. You want to be able to see this device. This is the Simel. It has been stationed here. This is the number 314. The number 15 was stationed here beginning in the late 90s, early 2000 time frame. This one has been here since about 2002, 2003. You can see that basically we've created a nice little permanent structure with it. This is a new addition since I put it up. The lead weight has been here for at least 15 or 10 years, and it's just to keep it stable. What's nice about the Simel is it's a commercial instrument produced by the company Simel in France, but it's part of Aeronet. And what's the advantage there is that everything that's collected by this gets stored inside a data logger inside the box, and then gets transmitted up to the GOES stationary satellite, geostationary satellite, and then downlinked to Goddard, where it's processed and available to anybody who wants it. The Simel does two big things. The first one is periodically, and if we're staying here for more than 10 minutes, we'll probably see it do it. It'll turn and try and point and find the sun. And it does that by hone it in. And that basically measures the transmitted solar irradiance. By using the Langley method, and by using calibrations they do in the laboratory, they know what they think the total solar irradiance would be measured by this instrument if they were outside the atmosphere up in space. So if you know what the measurement should be outside in space, and you know what the measurement is at the ground, guess what you can get? But just the basic measurement, especially if I took the ratio of those two measurements.
Transmittance.
Almost, not quite reflectance. Next one.
Irradiance.
Well, I'm measuring irradiance at the top of the atmosphere. I'm measuring irradiance at the bottom of the atmosphere. I'm going to take the ratio of the irradiance from the bottom to the irradiance at the top. So I'm going to get a number that I hope is less than 1. And so the three big things we worry about is basically reflectance, scattering, and reflectance, absorption, and transmittance. And so I'll get the transmittance in the atmosphere. I'm going to assume that I don't have absorption at this point. But the transmittance includes that absorption in it as well. But what's nice is, with the Langley method and others, we can get transmittance. There are multiple wavelengths in there. And because at the different wavelengths, the atmosphere behaves differently in terms of transmittance. At very short wavelengths, you are dominated by molecular scattering, aerosol scattering. You go to the longer wavelengths, the molecular scattering starts to go away and you're dominated by aerosol scattering. You pick a band at 940 nanometers and you're affected more by water vapor. You go to 550 nanometers and you're affected by ozone absorption. And by now combining all those data points together, you can decouple things and figure out what the aerosol optical thickness, so if you take the log of the transmittance, now you can go to optical thickness, get rid of the geometry effect, we can do it vertical. And so I can figure out what the vertical aerosol optical thickness is at multiple wavelengths, which then I can do some curve fitting and make a few assumptions, which allows me to compute it at all the other wavelengths where I might have absorption. And that allows me then to subtract off the aerosol from the absorption, which then allows me to get the absorption, which then allows me to get the absorber amounts. So I can get column water vapor from this, I can get column ozone from this, I can get total column aerosol optical thickness, and I can do that at a given wavelength, and then I can compute what they call the angstrom coefficient, which then tells me what it's doing at all the other wavelengths. So I now have what I need to run my radiant transfer code, all from that one measurement. What the SIML does that's also a nice thing, though, is it likes to spin around. If you look, and today's not the best day to do it, so on one of the clear days I'll try to remember to point it out, but if you can think back in your mind, and you look out on a nice, clear, blue, sunny day, and you look up and it's, wow, it's really blue, and then you look down towards the horizon and it's not so blue, that means that there's scattering that's happening differently as a function of angle. And it's mostly because the path length is longer, so we get more scattering, and it becomes whiter because all the colors scatter up equally at that point. Well, the SIML takes advantage of that. It measures basically looking straight up and all the way down the horizon, and it does that along the sun, along what they call the principal plane. And then they'll also do it, they'll look at the sun, and then they'll spin around in the azimuth, what they call the Alma-Cantor scan. And that gives you, that change in angle gives you information about the shape of the aerosol particles and the sizes, so that you now know how it's scattering as a function of angle. So you can also get instead of a nice simplistic angstrom coefficient, you can also get a true retrieval of the size distribution with something like the SIML. That second thing fails miserably here. It's too clean. You know, we just don't have enough aerosols to do that, so we have to rely mostly on the transmittance measurement. The University of Arizona will bring out another instrument that's a home-built that operates at a higher temporal resolution. It's also calibrated more frequently, and it's calibrated at the University of Arizona and on Mount Lemmon, and they'll use that primarily as the retrieval for the aerosols for what they do for their for the on-site collections. The SIML is what's used dominantly for the RADCATS collections. So this is an automated system. What's nice is these data are sent to NASA, and that's where Jeff gets it from. The Met Station data gets wired back over to the laboratory and then sent by phone to Arizona. Okay. So meteorological station gives me qualitative information about the atmosphere and the ground with the moisture sensor. SIML gives me quantitative information about the atmosphere, what it's doing, and it's mostly the atmospheric composition, aerosol, molecules, and absorbers. All right? So if we're doing reflectance-based calibration, the goal is to predict the top of atmosphere radiance, and I've just now figured out what's in the atmosphere. What's the last piece I need? Ground. I'm starting to think that everybody, they don't want to be on. You got to turn that thing off. Nobody wants to say anything. Everybody's pointing and they're quietly. It's like I'm seeing lips move, and so we'll go over and we'll look at the GVR next. But
can we maybe first can you shortly explain what the sensors are, or what is moving where? So what, or is it constantly? You know, it's not moving. So
it's asleep right now.
Do you have to task it, or?
No, it's completely automatic. And so in the middle of the day, it only collects data every 15 minutes at most. And it'll do, I forget when it does its Almacantor and principal plane scans. And then it'll do a collect every certain sun angle as the sun is setting, the sun is rising, to get a Langley plot. And so if we again stood here and waited, what would happen is it would first turn an azimuth, and then it would turn an elevation to where it thinks the sun is. And then there's another sensor in here that allows, it's a 4-cell silicon detector, and the algorithm in the data logger here works in a way that it equalizes the signal on all 4 cells. So it's a quad cell detector. And that fine tunes the pointing, and then it'll run through the filters and collect each filter and store it into a data logger box that's in this weatherproof enclosure. And then every hour that gets sent across to basically the transmitter that's in here that sends it to the antenna that sends it up to the geostationary satellite. So it's completely automatic, but the temporal sampling can be a little bit iffy. On a day like today, this would be a problem for a RADCAT's processing, because you would have some high variability that you'd have to deal with.
So how long does it take for complete measurement?
The direct solar, less than a minute. The Almacantor and the principal planes, they're significant lengths of time. Because you have to work through they work through 4 wavelengths, and they have to, and it's, measurement 1, 2, 3, 4, 5, and then it stops, and then it goes back, and it does the next wavelength. So it's, okay.
The sensor, or the filters on this, I'm wondering about the wavelengths that this is sensitive to. Is it all in just like atmospheric window type wavelengths, or is it at various points not sensitive to atmospheric windows?
It basically, the easy way to think of it is they're reasonably distributed from 440 nanometers to 1030 nanometers. And then there's one band that's purposely put in at 940 for water vapor. But the others are just sort of in there. You end up getting 3 ozone bands when you do that. And so that gives you enough information to at least do an ozone retrieval. And this was based on work done in it's been thought about and worked on since the 1970s and 80s. And so the bands have been part of the WMO selected bands, and so they're pretty standard. You can pick and choose when you buy one of your own, but if you're part of Aeronet, there's a certain set of wavelengths that you end up getting assigned. Right?
What kind of spatial scale do atmospheric constituents vary over?
Ooh, good question. And more importantly, how would you figure it out?
Yeah.
So in this valley, they're fairly, on a normal day, the variability would be, I only know it in optical thickness. It would be like, say, 0.005 in optical thickness at 550 nanometers in aerosol on a typical clean day. If it's really dusty, you might then get something that's more variable, but you would know that, and you wouldn't want to use the dusty day anyways. One way that you can assess that is you can look at, on a really clear day, what does the optical thickness do as a function of time. And you'll see it, if it's bouncing, that gives you an idea of the random kind of variability. Oh, here we go. I thought I heard it here. Yep. So now it's saying, where's level? Okay, I found level. There's my 0 point. Now I'm going to turn, and I'm going to go over there. And then it's going to go. Now it's cycling through the filters.
Pretty noisy. Sounds pretty noisy.
It's an operational outdoor system, and this one's been here for a long time. So now it's doing darks. And
Sound polluting the area here.
now, if you get lucky, it may end up doing either a principal plane or an Almacantor. If it does a principal plane, then Ian's going to have to move. If it does an Almacantor, some of us might have to duck. But the clouds are so bad that it's... Oh, and
So
I'm sorry, it does triplets. This is how it finds out if it's cloudy or something. So it's doing 3 sets of direct measurements right now. Sorry.
That was my question.
they send this one back to get recaled, or do they swap them out?
They swap. So I think what Jeff's going to do is he has a new one, so he's going to bring the new one here and then send this one back.
Is that like just the sensor or the whole station?
Basically, just the head has to go technically, but he'll send the data logger and the whole setup. He'll leave the box. Reflectance. Hopefully that's reasonably obvious. If you want to automate that, you have to come up with a mechanism for doing it. The way several of the groups are doing it now is they're taking that signal that we just looked at, and they're putting it on an enormously high tower, and they basically, when they do the Alpha Cantor scans, they also turn around and do a scan of the ground. And that gets them a nice measurement of the BRDF of the surface, as long as you assume that it's horizontally homogeneous enough that it's dominated by BRDF, and it gives them a measurement of the upwelling energy from the ground, which they can then convert to reflectance. And it's done multispectrally. When we were doing things here at Arizona, because this is Bureau of Land Management, getting a big tower in place, we knew that would take time. And again, as you've learned, I like to just do things. Jeff Chappell-Myers did early work with basically taking a set of light-emitting diodes, flipping the circuitry, so instead of them creating light, they became detectors, and then mounted them and put them out here at Railroad Valley and basically showed that, yea, verily, we can get a reflectance-based calibration that's of similar accuracy as the actual calibrations with just a little bit higher variability than doing what's done when you're on site. That then led to an improved set of instruments called what they now have as the ground viewing radiometer. That's an 8-band system that's out there right now. Covers it's 7 channels in the visible and near infrared and 1 channel in the shortwave infrared. And it's multispectral. Each band has its own detector, so the data are collected essentially simultaneously. There's a little bit of a delay because of the electronics, but it's essentially simultaneous. The height at which it's mounted is purposely chosen because there's a small angle to all the detectors so that they view the same piece of ground within some small amount. The area on the ground is about 10 centimeters in size, so it's not a huge area. We're finding out that might be an issue that we have to work on and figure out a way to either increase that, either by raising it or by increasing the angle. The field of view, though, if you increase the field of view to get a larger spatial, you now increase the angular view, which then you're now affected by BRDF. So there's trades of how you do the sampling. Because there are 4 of these around the playa, and they're separated in large distances, he can basically get a 1 kilometer by 1 kilometer area assessed. And the combination of all 4 overcomes, for now, as best we know, a small spatial sample. So if there's a heterogeneity problem affecting just one instrument, the heterogeneity problem is randomly distributed across the playa. It will not affect the other 3 instruments, so then it gets averaged out. And you end up with a pretty good data point. But it's still probably one of the causes of some of the bouncing we see from day to day in terms of the calibrations of the stable instrument. These data, as I mentioned, they're collected every 2 minutes. The things are painted black to try to limit backscatter effects. It's looking straight down. The optics are a little bit higher up. The snout is there to protect the front optics from splash and from dust and dirt blowing up in there and then caking onto the front optics. So the optical element is closer to the main white head than that black snout. The data loggers are inside here along with the power system. We want the LEDs because it was really cheap and inexpensive, so I was able to sneak it into another project. Nobody knew we were doing it. And then when we finally priced everything out, in the solar panel, which was smaller than this, the LED, the whole detector package was like 30 cents. The front piece of glass that we put on it was $5. The PVC tube was cheap, that was $2. So the whole radiometer ended up being $10. But still of that, the detector package was a tiny part of it. The batteries were $25. The solar panel was $75. The data logger was $100. We quickly said, this is dumb. We're cheaping out on the most important part of the system. So that's why we opted for more detailed systems. Jeff came up with a preliminary design before this one that was silicon-based that got rid of the LEDs and made the detector package more reasonably priced in terms of it being $300 out of a $500 package instead of $10 out of a $150 package. So there's that trade balance you should always keep in mind when you do things. We we sometimes forget that we get cheap in one area, and you might spend 7 weeks in order to get a 50-cent piece of equipment to work. Well, your 7 weeks of time is really valuable. Don't ever forget that. So this is looking straight down. Sun's moving, so they can get some BRDF information from that. But the calibration here, again, because it's nearly Lambertian, the advantage is if you have automated data you've been collecting all the time, you just wait until the satellite you want to calibrate is looking almost straight down. So you get away with that. They have another instrument I forget where he's putting it, that they're using for GOES R. And it's now pointed basically like this. You can do the Cam Newton thing for you football fans in America. It's the arrow things. But basically it's pointing, GOES R is over there somewhere and it's looking at an angle. And so they try to match the angle. And that gets rid of the dominant error source in terms of reflectance retrieval from a non-Lambertian problem. So you get that view angle done properly. So it's a really simple instrument, but it's measuring radiance coming up from the surface. The SML data is used in the radiant transfer code to compute the downwelling irradiance on the surface. And then that ratio is what you use to get to reflectance, which is nice because this is a traceability path that's completely different than that NIST traceability through the reflectance panel. So when Jeff comes out here and does Landsat 8 using the panel and he's doing a ratio measurement, he gets one answer. When he does RadCats, he gets another answer. He can compare them. He's getting very close to the same answer, which is incredible because they're following two completely different traceability paths, which is a really phenomenal result. So I think he doesn't think it's as cool as I do, but he'll figure it out soon. Any questions?
How much did this one cost?
You can either view it as infinite in cost or zero because it's part of a grant, and so the actual the labor and everything is you have no idea really what it took. The parts are. We can ask Jeff, and Jeff can ask Nick Anderson who put it together. I would be guessing. I know roughly. I ended up. One of these was covered by a grant from NASA, so I could have data myself if I wanted it. And that's also what led them to. This is the basis of the cat sitter design, and so that was the idea: was we build another one that's a better version of this, and then follow on as cat sitter. And I can tell you roughly what the grant was worth, but I don't know how they broke out the equipment and the labor. It's probably on par to a SML. I'd say a little bit more expensive because they're one-offs and things like that. They don't have volume as part of their system.
Which SML?
That's SML. Anything else?
How much is the calibration coefficients when you use these radiometers?
Currently, there are only a few cases where there's a statistically significant difference at the 95% confidence interval, with the knowledge that the error budget that Jeff has on this is plus minus 4% absolute, and the reflectance based with people on site is 2.5%. So when you do that combination, they all agree. And that's the real power of it. You now have something that you do not have to be on site for. And I think we can tease these down to lower numbers, but it's going to come with time and expertise that we don't have yet. So, for instance, if we go to Chile and put a site in, we could probably we could have better numbers, because as you put new equipment with new knowledge and better placements, we go to Australia with a site that's better selected for its heterogeneity effects and things. You probably will get better uncertainties.
This instrument is also calibrated periodically?
Very good question. So the way this is calibrated is it has to be pulled from its mount and taken back to Arizona, put in front of the sphere, and then brought back. So one of the reasons why we built Cat Sitter was, and you'll see Brian Winnie, maybe have a break or something, I'll take him out and have him show you what he's doing. But we'll have the transfer radiometer, which was calibrated in the laboratory, and we know what its values are, looking at a sample, in this case it will be a barium sulfate panel, and now the panel will go underneath the radiometer, and it'll go underneath the Cat Sitter. And we also will have a gray tarp that we'll put under there. So the gray tarp is close to the reflectance of the playa. The white panel panel is one that's used for reflectance based calibration. And looking at comparing those two measurements, we should get the same radiance. And there'll be a slight time difference you'll have to take into account, but if we flip back and forth, the radiance reported by cat sitter and the radiance reported by the GVR should be the same. And if there are large differences, then they know to pull it and take it and calibrate it. If there are small differences, then they know to watch it. So this is a way that they can either calibrate and adjust the calibration in the field, but also know if there's a system that's malfunctioning. And they're tracking the data as it comes down from the mobile laboratory through the satellite phone. And they can see, for instance, as they process data for a given set of sensors, if all of a sudden this one starts to look odd relative to the others. So over time, the instruments are doing this, and all of a sudden one instrument does that and the rest do this, then this one is suspect and needs to be checked. But it has to be pulled and taken back. That's the problem. So that's why they're trying to get an additional one so they can just swap them in and out so they always have the same number of radiometers operating. Calibrated in an absolute sense against each other. But you start talking about having 20, 30, 40 instruments as part of a constellation, there's just no way that you can have people out at a site characterizing it well enough to do that. So you need something where the people who are tasking the instrument can task it at their convenience and find a way to get the data easily, and that's what RadCalNet's all about. So. Nope, good.
Is it a RadCat?
This is RadCats, which is also part of RadCalNet.
RadCalNet.
And it's called RadCats. Yeah, we need to start heading back. RadCats because the University of Arizona is the Arizona Wildcats. So this is radiometric calibration test site. It's RadCats. So it's Arizona RadCats, which are the Wildcats. It's my fault. Cat sitter is my fault. Cat sitter is here. It's supposed to take care of the RadCats. So it's a cat sitter. The buildup underneath. And that's one of the things they're worried about right now is even out in front of the instrument, some of the others, they're starting to see dunes starting to form because of the wind patterns. And we think that's what's causing some of the heterogeneity problems with the measurements. And then the question becomes, so do you just go in periodically and just grind it down and sweep it off? Or do you just take the beating? And so we're at that point. What's nice is we're seeing these effects because they're very small. And how you then correct for them to get the error budget better is what we're talking about, not whether or not the value is even close to right.